This is another example where drawing the picture might make you a little bit smarter. And I think in this case, there might be a little bit too much information. Like maybe we don't need all these squares. And then we should drop the stuff that we don't need. But we don't know that right away. So how do we even start drawing this? Well, the square in the corner, in the left bottom, sort of engages with the rectangle at both ends. And that establishes sort of the directions. It's just going to be perpendicular to this, parallel with this, perpendicular to this, parallel with this. And then here is this other thing. Okay. So I'm not sure if we're even going to use this one. This is just kind of sort of hanging there. It doesn't interact much with the rectangle, unlike all these others, right? There is this point here, there's this point there. Okay. So we know that these sides are 1, and we can always chase around angles, because whenever you have rectangles tilted in a rectangle, you can run around and the whole thing is covered with similar triangles. That does happen here. This here is an angle alpha. Then this is 90 minus alpha. This is 90. So to add to this, to get 180, that has to be 90. So this is alpha again. This is that other angle again. These two angles are vertical. This is alpha again. There is some lovely stuff going on. This angle is 90 minus alpha, if we call the orange one alpha. And because of this, and now to that angle, we add something that makes it right again. This is what you can visualize, that someone grabbed this angle and rotated it downward by 90 degrees, right? This angle, this rotated into this, and this rotated into that. But I just like this fact that if you add any of these two angles, you have to get the same 90. And then, of course, this is the complement of alpha, and this is alpha again. And so we have lots of right triangles, all similar to each other. There's nothing going on here. We might have to draw some lines. Who knows? Maybe the key is that if you keep going here, that would hit the... Oh, I didn't think about that. We shouldn't assume that just because it would be nice that this line, if we kept going, would hit that vertex. But it looks like that's a definite possibility. I didn't think of that until now. Okay. So we need sides. We're going to have to find, for the area of the rectangle, we need both sides. So there's no way around. We need sides. And so it looks like Pythagorean theorem and or similar triangles will play, but we need more than one side. So you have to stare at this picture until you realize that there is one triangle on this picture where we know both sides. And we're going to set foot on there, and from there we're just going to spread similar triangles and get everything. And the triangle where we know everything is this one. And don't think I found it all that quickly. You see, this here is one of those similar right triangles where the shorter side is 1 and this longer side is 2. This is the triangle that I call the domino triangle, where not the sine is half, but tangent, right? So this is going on. And so all of these similar triangles look like this. The shorter leg is x, then the longer leg is 2x. And if you run the Pythagorean theorem, you're going to find that the hypotenuse is square root of 5 times x, right? 1 squared plus 2 squared is 5. And then the rest is going to be ratios. For example, what we already know that if this is 1 and this is 2, then this side here is square root of 5. That's not bad. We almost have the entire horizontal side. And then to find the rest, we're kind of forced to look at this line segment, which sits in this similar triangle. But it's not congruent because even though it has a side too long, it's the hypotenuse, right? These two triangles are similar, but they're not congruent because although both of them has a side that's 2 units long, it's longer leg in this triangle and it's the hypotenuse in that triangle. But that means we can compute stuff. It's just a matter of how you want to set up the ratio problems. Sometimes you set up ratio problems and equations, but sometimes you get away with scaling stuff. So for example, you can say, well, I want to know these guys. How do we get from square root of 5 to 2? We can say that from square root of 5, which is the hypotenuse here, to get to a hypotenuse of 2 there, what we're going to have to do is divide by square root of 5 and multiply by 2, right? That's pretty straightforward. If we multiply square root of 5 by that number, we're going to get 2, which means that that's going to be the scale factor or magnifying factor for the other two sides. So if this side is 1, then this side is going to be 1 times 2 over root 5. And if this side is 2, then this side is going to be 2 times 2 root 5. You know, I think when I was a student, I didn't do this. What I did was sort of brute force it, but I said, I don't know. I just know that if this is a, this is 2a, and then a squared plus 2a squared is 2 squared. And then solve for a. I think that was the most straightforward way. So you can do that too. A squared plus 4a squared is 4. 5a squared is 4. A squared is 4 over 5. And so a is 2 over root 5. That is the same 2 over root 5 that we found by scaling. And then the other side is 2 times 2 root of 5, so that's 4 over root 5. Okay, so that's pretty good. We have the horizontal side. And then from the vertical side, we have a whole big chunk. It's 4 over root 5. And yes, these numbers are not pretty, but they are all not pretty the same way. It's all having to do with root 5. So there is hope for nice numbers. And then what's left here is this shortest side in this similar triangle in which the hypotenuse is 1. Well, that's going to be easier because we just figured out a similar triangle with hypotenuse 2. So that means just grab this triangle and divide all the sides by 2. Again, you can call it b and then b, 2b from the Pythagorean theorem. B squared plus 2b squared is 1 squared. You will get it. But also we can just use ratios, obvious ratios. So the shorter side in the double twice as big triangle is 2 over root 5. So this should be 1 over root 5. And then we don't even need this, right? Now let's see, the vertical side is 4 over root 5 plus 1 over root 5, which we have a, right, 4 over root 5 and 1 over root 5, which we have the common denominator is 5 over root 5, which is actually root 5. That's kind of cool. You can multiply upstairs and downstairs by root 5, and then you're going to get a... So here it is. This is something I want you to notice. So as it turns out, we're not going to have to rationalize this. This is perfectly fine, but I'd like to show you something that you should notice. 5 over root 5. If you rationalize it, we get 5 root 5 over 5, which is just root 5. And then look back, like, yeah, it kind of makes sense, but we don't need to do all this because 5 divided by root 5. Remember what root 5 is? Root 5 is the number that if we squared it, we get 5. So this is square root of 5 squared. over square root of 5 to the first power. And then you just cancel out the root 5, and there it is. This, you do this thing 2-3 times, and then you're going to recognize that this is always just root 5. But actually, I've solved this problem before, so I know we're not going to need to rationalize it. So this is going to be perfectly fine. So the horizontal side is root 5 plus 2 over root 5. And that's the one where I decided to rationalize it, because the long one, square root of 5, that doesn't have that irrational denominator. So we have to add root 5 plus 2 over root 5. Let's rationalize this one by multiplying upstairs and downstairs by root 5. So then we get root 5. This is the horizontal side. This looks intimidating, but it's square root of 5. You can factor it out. And how many times square root of 5? 1 plus 2 over 5, right? Square root of 5 times 1 plus 2 over 5. 5 over 5 plus 2 over 5, that's 7 over 5. So it's 7 over 5 many times root 5. So that's why we didn't have to rationalize the length of the vertical side, because for the area, we're going to multiply 5 over root 5 by 7 over 5 times root 5. See, so 1 root 5 upstairs, 1 downstairs, that's good in multiplication. And then 5 cancels out 2, and I find that amazing that we got 7. It's such a prime number, it's not related to 5 in any way. That's not something I would expect as a result. Thank you for watching.